Good morning, everyone. I hope you can hear me. I'm John Simons, Head of Products at Cambustion. I hope everyone is well and safe this morning in this slightly complicated global situation we're in, to say the least. Good afternoon to most people. It's morning here. It's 8 o'clock. It's a slightly grey day in Britain. We've had a lovely spring so far. It's been really sunny. In fact, I think it's been the sunniest spring on record, but it's decided to rain today, which is how I expect most people expect it to be in England. It often is. Okay, well, we'll start then. So I will share my presentation and then I will switch my webcam off. This will be recorded, by the way. We will send a link for the recording in due course. And please feel free to ask questions using the question facility. Some of those we'll answer along the way if we can. Otherwise, I'll answer them at the end. Okay. So today I'm going to talk about the Aerodynamic Aerosol Classifier, classifying particles from 25 nanometers to 5 microns without charging them. And I see we've got some AAC users on the line, which is great. And there might be some new features and software features that you can find out about. Okay, the contents of this presentation are going to be as follows. I'm going to start by just giving an introduction to Cambustion briefly for those of you who are not familiar with us. I'm then going to introduce the AAC, go into some of the technical details of its operation, and then go to an evaluation of its performance. I'm then going to spend the rest of the talk talking about applications of the AAC, which include filter media evaluation, inhalation studies, determination of density of aerosols, optical particle counter calibration, condensation particle counter calibration, aerosol mass spectrometer calibration, particle charge determination, and selection of particles by their morphology. So Cambustion was founded 33 years ago as an offshoot of Cambridge University Engineering Department by Professor Nick Collins, and some of his students. The initial product was a fast response flame ionization detector for detecting hydrocarbons in real time from an engine, and more products followed, including in the last 20 years particle and aerosol analyzers. We later set up an emissions consultancy division for engine testing. Our headquarters is in Cambridge in the United Kingdom, hence our name, Cambridge and Cambustion. We have a sub-office in Shanghai, and we have representation in France, Germany, India, and Japan. The other territories are successfully served from the UK. We're an independent private company and remain so, and we pride ourselves on our highly skilled employees, which are mostly at graduate and PhD level, and the excellent technical support and application support that such people can give our customers. We have strong links still with universities, both in Cambridge and all over the world. We have valuable collaborations and sponsorship of relevant projects such as PhDs. So our aerosol products, briefly, we started out 20 years ago by making the DMS 500, which is still the world's fastest electrical mobility sizer with a 10 Hertz data rate and, crucially, a 200 millisecond fluidic time response. The CPMA is a mass classifier. The AAC, which we're talking about today, is an aerodynamic diameter classifier. We also have a unipolar particle charger, which is in its second incarnation as of this year, electrostatic precipitator for removing charged particles from an aerosol stream, and a smoking and vaping machine. Okay, onto the AAC. So the AAC solves two problems in aerosol science, which have been around for a long while. First problem is, how do I select a monodisperse aerosol without getting multiple and zero charging artifacts, as I do with a differential mobility analyzer? The second problem it solves, if I want to use aerodynamic diameter, how do I select a monodisperse aerosol using aerodynamic diameter? And that's an AAC on the right, by the way. So traditionally, to get a monodisperse aerosol, so-called, you have used a DMA, differential mobility analyzer. This uses electrical mobility to classify particles, which is the motion of a charged particle in an electrostatic field. And that relates not only to its size and shape, which is what you want to measure, but it also relates to the number of charges on the particle. This suffers from multiple charging artifacts. So smaller particles with one charge may end up having the same electrical mobility as a larger particle with more than one charge. There's less transmission than you would like at small diameters due to the charging efficiency. So you normally use a radioactive bipolar charger with a DMA, and for 100 nanometer particles, there's only a 20% chance of that particle gaining that one charge that you want. Most of the particles will gain either no charges or in fact a negative charge, which won't pass through the DMA. And quite a lot of the particles will also gain 2, 3, 4 charges, particularly at larger sizes. That introduces uncertainty in your measurement. The correction is normally performed in an SMPS using an inversion algorithm, but you can't eliminate that uncertainty, particularly if you're using it just as a classifier. The SMPS is well established, the correction algorithms are pretty good, but if you're using your DMA as a classifier, you have to take steps yourself to reduce the likelihood of there being multiply charged particles. That normally involves being careful about the size distribution that you start off with and making sure you take your cut with your DMA from the large particle size to minimize the probability of there being even larger particles in the population to select. So with the DMA, what you want is on the left, which is 1 peak. What you actually get is the peak at 1 charge, but you'll also get peaks at 2 charges and 3 charges if you're not careful, and those will have larger sizes and will skew your results. With the AAC, you just get 1 peak out. It doesn't involve any electrical properties of the particle. It's purely an aerodynamic diameter measurement or selection. Aerodynamic diameter, I'm sure, is familiar to most of you. It's perhaps best explained by the use of an impactor, where particles accelerate through a nozzle. The largest particles are unable to follow the gas streamlines due to inertia and get impacted on a plate, whereas the smallest particles just pass straight through. So we have large particles going splat onto the plate, and the small particles are able to follow the streamlines. And you can see here's an impactor on the front of a DMA to remove the large particles. Aerodynamic diameter of an irregular particle is defined as the diameter of a spherical particle with a density of 1,000 kilograms per cubic meter and the same settling velocity as the irregular particle. Aerodynamic diameter is a key size metric for many aerosol scientists, especially those working in inhalation, health effects, and filtration. Classified by aerodynamic diameter, rather than just determining the sizes of particles in an aerosol stream as you would with an ELPI or a cascade impactor, it's often desirable to be able to classify them for further online analysis. So a cascade impactor you can analyze the particles, but they've splattered on the plate. With an AAC, the particles are still in the aerosol phase when they leave the analyzer. So a regular impactor, it can be thought of something that allows smaller particles to pass through. A virtual impactor can be thought of something which allows larger particles to pass through. And now we have the AAC, which can be thought of as a sort of band pass. It allows particles over a finite size range to pass through. So how does the AAC work? Well, it has many similarities with the DMA. It has a sheath flow, which passes along a column, and smaller particles match the sheath flow sooner. Larger particles do not match the sheath flow and end up being splattered on the wall. It does not rely on particle charging. There is a transverse force, as in the DMA, but it's not an electrical force. It's a centrifugal force. So the entire classifier is spinning. So you could think of it like a rotating DMA without an electric field, but it does have the sheath flow. So we have some particles entering here into the sheath flow. So the larger particle ends up on the outside wall, the smallest particles end up carried over the sheath flow, and the particles that you want end up coming through this slit and out of the AAC in its monodisperse channel. Here's an animation of that slightly more slowly. With sheath flow, we put in a polydisperse aerosol. The small particles get lost with the sheath flow. The large particles end up on the walls and have to eventually be cleaned off when you clean the classifier, as with the DMA. And the particles you require for the speed that the classifier is set to end up coming out of this slit here and can be further analyzed or counted as required. So this is the Wiedenhofer charge model for bipolar charge distribution, usually for radioactive sources. The particles, when you're using a DMA that you're interested in, are the singly charged particles, because the uncharged and the negative charged particles won't pass through a DMA, at least one that has a negative polarity on the rod, and these particles with multiple charges, 2, 3, 4, and 5, will just skew your results. So you want to minimize that, and you want to concentrate on the particles with one charge given here. Now, if we look, say, at a 100 nanometer particle, only 20% of the particles you start off with will meet that criteria of having one charge. So all the other particles are wasted. So most of them are either uncharged or have a negative charge, and a few of them at 100 nanometers, although increasingly as you get larger in size, have multiple charges. So that means that the total transmission efficiency of the neutralizer plus the DMA is actually not very good. Now, the DMA column itself will have a very high transmission efficiency. There's not a lot of diffusive loss in it. It's quite a big channel. But when you put the neutralizer on it, which you have to use with it, because you can't just use the column on its own, then you lose an awful lot of particles in that charging process. They just don't pass through the DMA. So if you look at the total transmission efficiency of a long column DMA with a neutralizer, it peaks, as I say, at about just over 20%, at just over 100 nanometers. Whereas if you look at the efficiency of the AAC, it is always higher than the neutralizer and the DMA. So you do have some tail off in the transmission efficiency of the AAC at small sizes, and that's due to diffusion, because there's quite a small gap between the inner and outer classifier walls, and you do naturally lose particles by diffusion, but you always win over the DMA because you don't have to charge the particles. So here's the technical detail. The mathematics or the physics of the AAC is quite simple. And this shows how aerodynamic diameter is related to the physical properties of the AAC and the carrier gas. So here we have the sheath flow, the volumetric flow of the sheath flow. Here we have the speed of the classifier, and here we have the radii of the inner and outer cylinders that form the classification region, and L is the length of the classifier. So you can see there's a traceable physical relationship between aerodynamic diameter and the physical characteristics of the classifier. There are some gas properties involved here, such as the gas viscosity, and this is just a unit density, which is from the definition of aerodynamic diameter. This is 1,000 kilograms per cubic meter by definition. This is the cutting and slip correction, which is also a correction that needs to be made for the smaller particles in the DMA, and that forms part of this too. So it's quite a traceable, easy to understand measurement in that regard. In terms of resolution, i.e. how wide the transfer function is, that the width of the particle distribution you get out, it's exactly the same expression as for a DMA. It's the ratio of the sheath flow to the sample flow. So all we have to do, all the user has to do, is to select a resolution and a size, and then the mathematics will just calculate what the speed is, and the classifier will run at that speed. Specifications, 25 nanometers to 5 microns verified. We say that at the moment. It's actually quite hard to verify it with particles larger than that. Theoretically, given the dimensions of the classifier and the speeds we're running at, it should be able to go up to 6.8 microns. The sample flow rate, 0.3 to 1.5 liters a minute to match common CPCs. Sheath flow rate, roughly a ratio of 10 to 1 to the sample flow rate. Spins up to 7,000 RPM, so slower than the CPMA that some of you may be familiar with. As a result, it's quieter as well. Built-in touchscreen and various I/O options, which I'll come on to. It's compatible with a wide range of CPCs if you want to use it to produce aerosol size spectra. These charts show the permissible aerodynamic diameter as a function of resolution, also as a function of the sample flow rate. These are given in the brochure. These are the sort of operating maps. And again, the software will tell you if you're in the permissible operating range. As I say, the instrument has a built-in touchscreen, so it can be operated completely standalone. Here's the scanning mode, where data is recorded to a USB drive. And it also has various remote control options. So there's a PC application, which you can run on your desktop or laptop, communicating with the AAC over USB, Ethernet, or serial. There's a built-in web server or VNC client where you can actually just share the AAC's front panel screen. You can include it in your own data capture programs. We supply an application programming interface, DLL, and various text commands that you can send over USB, Ethernet, or serial. And we've even got good old-fashioned analog inputs where you can control the various functions using an analog voltage. We also can provide an optional aerosol flow meter accessory which goes after the AAC to measure the sample flow. So in many cases you may know the sample flow because you've got a CPC that's doing the measurement. In some cases you may not know, and this allows you to measure the sample flow, which only affects the resolution of the instrument, but if you want to run at a constant resolution and you've got a varying sample flow, then it may be a good idea to measure that flow. Okay, as I think I've mentioned several times, the instrument scans. That's rather like, is now rather like an SMPS. So you have an AAC, which selects the aerodynamic diameter, and then you have a CPC downstream of it, which measures the concentration. And the measurement of concentration is fed back to the AAC. The AAC changes size. The CPC responds in proportion to the concentration at that size, and a spectrum is built up. Now, in the beginning, we had a step scan function built in, which for those of you who are old enough, if you remember the DMPS, which was the first scanning instrument based on the DMA and the CPC. This was a step scanning instrument. This is exactly the same. We set the AAC size, we measure, we allow it to settle, and then we measure the concentration of the CPC. We then change the AAC size again, allow it to settle, measure the CPC, and step the size this way. This is quite slow. So since 2019, we've implemented a continuous scan, and this is more like an SMPS, in which the AAC constantly changes its speed over the scan, and the CPC constantly takes readings, and the data is corrected for the lag between those two devices. It's like an SMPS. It's a faster scan, and it gives you a higher resolution as well. Okay, how does it all perform? So first of all, what does the monodisperse output look like? So we have a DOS oil aerosol nebulizer, we put it into the AAC, and we take an SMPS scan for smaller particles, or a Pallas-Wellas size spectrum, which is an optical sizer for the larger particles beyond the scope of the SMPS. So an example for smaller particles, here we have 50 nanometers, and bear in mind the SMPS measures by electrical mobility diameter and the AAC measures by aerodynamic diameter, so we have to do a slight conversion for that. But as you can see, we get a nice sharp monodisperse output in the right place. And for the larger particles, this is 4 microns, which you just simply can't do with the DMA, and you certainly can't measure it with an SMPS, measured with the Pallas-Wellas. So overall, the size accuracy was evaluated at smaller sizes using polystyrene latex spheres, which we aerosolized with either an electrospray for smaller than 100 nanometers or a Collison nebulizer for larger than 100 nanometers. So we take the aerosol source and we're doing a step scan of the PSL here with the CPC. And the results show that we're certainly better than 10% on the PSL. There's considerable error in doing this experiment actually with PSL. If anyone that actually uses it will know in terms of its way it's prepared and everything and how careful you have to be. So I think that's quite satisfactory. And of course, there's a conversion there between the mobility diameter that the PSL is set to be and the aerodynamic diameter using the density of the PSL to do that conversion. Transmission efficiency, as I said at the beginning, the DMA transmission efficiency, when you include the neutralizer, can be quite low. So here's an example of the DMA, both high flow, which is 1.5 liters a minute, and low flow, which is 0.3 liters a minute. The AAC is up here for high flow and low flow. So theoretically, the AAC maximum transmission efficiency is 0.9. You could never do better than that. And here we're doing about 90% of, well, we're doing about 90% of what we could do. So we're actually reaching 80% here, which is pretty good. And of course, at smaller particle sizes, you get natural diffusion loss, and it's consistent with diffusion loss, that loss pattern. The AAC losses across the board are lower than the DMA system with the neutralizer. If you're doing a scan with the AAC, we correct for those losses as the DMA does with the diffusion as well. So there's an algorithm to correct for diffusion losses built in if you're doing a scan. Okay, comparison with an ELPI. So as you'll probably know, an electrical low pressure impactor by Ducati is a fast aerodynamic diameter sizer, produces a size spectrum in real time. We've got one here. The data from that is in blue at fairly low resolution, and we have the data from the AAC at low flow and high flow in orange and silver respectively, and you can see a respectable agreement between those two analyzers. This is a DOS aerosol coming straight out of a constant output atomizer. Many people are interested in electrical mobility, or rather mobility diameter. The AAC provides an automatic means of converting between aerodynamic diameter and mobility diameter. You simply have to enter the density of the aerosol that you're interested in, and it will do the conversion for you. That's both on the front panel when you want to select a size, and also in the data file, the scan file, it will produce a mobility size spectral density column and statistics on that spectrum. So we need to do that to compare with an SMPS, because the SMPS measures by mobility diameter. So here we have a comparison. We have in the squares, we have the SMPS, and in the circles and the diamonds, we have the AAC at low flow and high flow. Of course, the SMPS measurement stops at a few hundred nanometers. It's not practical to use it beyond that. So the SMPS data doesn't go further than this, but you can see an excellent agreement when you do that conversion between the two size metrics. So we developed the continuous scanning last year, which reduces the scan times considerably and increases the resolution. So here we have a comparison between the step scan and the continuous scan, given with a dotted line and a dashed line respectively. We have a DOS aerosol here, and as you can see, the two lines overlap very well, and we have up scans in blue and down scans in red. With the real aerosol, this is in the R&D lab at Cambustion, so people start to go home at about 6 o'clock. When we start doing continuous scans of the ambient air, and by the time it gets to 20 to 10, that was quite a late night, the air had cleaned considerably because the doors hadn't been opened so much into the outside world where all the pollution is. And that's really only possible with the AAC when we developed fast scanning. Okay, on to the applications now. First of all, filter evaluation, which is kind of topical at the moment. So normally filter media are tested for their size-dependent filtration efficiency by using a DMA to cut the aerosol. And we thought, well, let's try and use an AAC. For two reasons. One is that you don't get the multiple charging problem that you have with a DMA, so you get less artifacts in the measurement. And the second reason is that aerodynamic diameter is an interesting metric to use in filtration. So we have two face masks here. We have an FFP1 by 3M, and we have a Honeywell N95. And we're going to test a small section of the media here. So the schematic's on the next diagram, but basically we have some aerosol generation here, which is salt, or in the further paper, cast aerosol. We have a rotating disc diluter to adjust the concentration to suit the CPC. We have the AAC to select by size. We have a filter paper holder, which contains a section of the filter media. We have various pumps and flow meters to put the flow through, and we have a CPC to count the particles. So we cut samples from the face mask and seal them in a 47mm filter holder. TSI CPC, the same CPC is used for up and downstream counting for consistency. The procedure here is consistent with the ISO 16900-3 standard for testing filter media, except we're using the AAC rather than a DMA. So we've substituted the AAC in here. We've also got a DMA as well, and we do a back-to-back comparison. So the aerosol comes in from the atomizer. We select by size, either aerodynamic or electrical mobility. In both cases, we neutralize, and that's because the standard says we must. And it's a good idea to do that even though the AAC doesn't use any electrical properties of the particle, because the atomization process charges the aerosol, and you don't want any charge on the particle to affect the filtration efficiency, or if you're actually weighing filters later on, which we didn't do in this particular study, that can affect the weighing just by using the electrostatic forces affecting the balance. So bring the sample in here into a larger flow of air, which is mass flow control, which goes through the filter holder at standard filter face velocities and comes out the other end via the pump. and then we switch the CPC between upstream and downstream to make a filtration efficiency measurement. So we're using salt particles in this section of the study. So on the left-hand side, we have the 3M mask, we have the AAC results in red, and we have the DMA results in blue. And you can see for the smaller particles there is a difference, but that is because of the multiply charged particles in the DMA. So we're getting larger multiply charged particles. So where we think this is 50 nanometers, we've got some particles in there which are larger than that. And those are less efficiently captured by the filter media because they're larger and they're less caught by diffusion in this diffusion regime. So the concentration appears to be, or rather the penetration appears to be higher than it actually is for the DMA. You don't get that error with the AAC. In both cases, we convert it into aerodynamic diameter because we know the density of the test aerosol. If we move on to the Honeywell mask media, then we also see a deviation, at this time at large particle sizes. So this is the larger multiply charged particles of the DMA, which are more efficiently collected by interception. So we're on this side of the, of the diffusion interception mechanism curve, if you like. So you can see that if you use a DMA, you have to be very careful with what you're doing with your test aerosol that you start with and sample from the right-hand side. And if you're not, you'll get artifacts in there. You don't have that problem with the AAC. Also, another reason for maybe using an AAC for this is you get a much higher throughput. So if you don't have much test aerosol, if it's something slightly exotic, like say a virus, you may not have so high a concentration. You can get up to 5 times more concentration going through your filter if you use an AAC because you don't have the charging inefficiencies of a neutralizer. My colleague Simon Payne produced a paper on this some time ago. He will be giving a future webinar at a date to be determined, details at the end, showing more of this data on face mask media measurement and indeed room air filtration measurements as well. So on to inhalation. As many of you will know, will be experts in this, the location of deposition in the airways is a function of aerodynamic diameter. So if we want to do size resolved deposition studies in the lungs, let's use aerodynamic diameter for that. So let's start off with a broad aerosol. Let's cut it by aerodynamic diameter with the AAC, so it's monodisperse, and then inhale it into a subject. And when they exhale, you know that you can do online analysis of the exhale fraction for a given known inhaled aerodynamic diameter. Or if you're interested in systemic effects, you know that person has inhaled a certain aerodynamic diameter, and you can work out where in the lung it will be deposited, and you can work out the efficacy of that drug or whatever for that particular part of the lung. Determining density. So there are now 3 classifiers that you can buy for which cover a lot of the morphological properties of aerosol particles. There's the AAC for aerodynamic diameter, there's a DMA for electrical mobility diameter, and there's the CPMA or APM for particle mass. These 3 are related by this equation, or rather their measurands are related by this equation. So we have this quantity here, which is actually relaxation time, which is directly related to aerodynamic diameter, and mass and mobility. If you have any 2 of these analyzers, you can measure the properties measured by the 3rd analyzer if you use them in tandem. So if you have an AAC and a DMA, you can actually measure mass and hence density information. And likewise, if you have an AAC and a CPMA, you can yield mobility information. Now, of course, normally people make measurements of density and mass with a CPMA and a DMA. The advantage of doing it with a DMA and an AAC is that the AAC doesn't need a multiple charge correction as the CPMA does. The DMA needs one anyway, but at least you've only got to cope with 1 rather than 2 of your instruments requiring a multiple charge correction. So this was done actually on a prototype AAC 6 years ago by Farzan Tavakoli and Jason Alford in Canada, and we have 3 aerosols here. We have 2 spherical aerosols, DOS in red, PSL in blue. So the PSL has a slightly higher than 1 density, and the DOS has a slightly lower than 1 density, and you get that, and it's constant by mobility diameter, as you'd expect for a spherical aerosol. When you put soot into this setup, the density of the soot decreases with mobility diameter, which you expect as the particles become more fractal as they get larger. Why is measuring the density of aerosols important? Well, it turns out to be quite important for climate change. So the density of black carbon in the atmosphere tells you something about its mixing state, and that's the amount of the particles which consists of black carbon, and the amount which doesn't consist of black carbon consists of other things absorbed onto the black carbon. And that tells you how absorptive or reflective the particles are, and that can tell you the contribution to radiative forcing and climate change of black carbon in that particular environment. And there have been several studies, actually mainly using a CPMA for determining the density of aerosols in urban areas and the effect on climate change, but that could be done with an AAC. So on to various instrument calibration things now. So optical particle counters, I've said, for example, a CPC. I'll come on specifically onto a CPC later, but general OPCs tend to count the larger particles, because for light to interact with a particle, those particles have to be larger approximately than the wavelength of light. And that means we're generally dealing with larger particles for OPCs, and that means with a DMA we're dealing with multiple charges. So if you're trying to calibrate your OPC as a function of size using a DMA, you've got to be very careful about multiple charges, which will be larger than you think they are, the particles. So if you try and use a DMA to select particles for calibrating an OPC, you can well end up with all these multiple charge peaks, which will skew your result because these are not the size you think you are. And you have to be careful in selecting the original test aerosol or do a reasonably complicated charge correction afterwards. If you just use an AAC, you just get one peak. It's as simple as that. And you can do that up to several microns as well. So Sangnapur and Alford published a paper at the end of last year that shows a very good worked example of doing this. So CPC calibration for smaller particles, condensation particle calibration. Well, why might you want to use an AAC rather than a DMA? A good practical reason is that you don't need a neutralizer in an AAC. And if you're trying to calibrate a CPC, let's say you're doing an engine test lab, so we're actually going to use an engine CPC here, then you may not be able to bring a neutralizer into that workplace. They may not have a radioactive license. You may not have a radioactive transport license, depending on what territory you're in. It varies across the world. Using AAC, you don't have to worry about radioactive licenses. Okay, so here we have a Collison nebulizer. This is cesium chloride. I'll come on to why cesium chloride and not sodium chloride in a bit. We have a diffusion dryer to dry off the water, leaving the solid aerosol behind. AAC, various makeup flows, and then we split into this engine exhaust CPC and a normal 3775 CPC. Now, the engine exhaust CPC, as you may know, has a D50, so a 50% transmission efficiency at 23 nanometers, and that is to match the so-called PMP or R83 legislation for automotive emissions that at the moment discounts the particles smaller than 23 nanometers because they might consist of volatiles. So that's quite a good example to use because you've got a known prescribed transmission, measurement efficiency curve for that CPC that we can check. The 3775 CPC is good down to 4 nanometers. Why cesium chloride? Well, we want to get down to quite small sizes here, quite small mobility sizes, in order to make this check of the measurement efficiency of that CPC. Now, the AAC's aerodynamic diameter goes down to 25 nanometers. However, because of the relationship between aerodynamic diameter and mobility diameter, if you use a dense test aerosol, you can get down much lower than that in terms of mobility diameter. Now, cesium chloride is a salt, and it has a density of 4 grams per cc, so 4,000 kilograms per cubic meter, which is almost double that of sodium chloride. It's basically non-toxic as well. I mean, I wouldn't drink it, but it's fairly good stuff to work with, and it will give you small mobility sizes. So that's good. So you can go down to 7 nanometers in mobility size with an AAC if you use cesium chloride as a test aerosol. Results, so there's a certain prescribed curve for CPCs, engine CPCs, and it's a 50% transmission at 23 nanometers and a 90% transmission at 41 nanometers. And you can see we're pretty much there in terms of that curve we get out. There are a few caveats to this. So this particular CPC has been previously recalibrated in the field using a cast soot aerosol and not the original manufacturer's calibration using emery oil. We don't know the butanol wettability of cesium chloride. It may vary from other test aerosols. Humidity is probably also a factor here, as it is for sodium chloride. The roll-off of CPCs may not only be a function of mobility diameter. There may be some direct effect from aerodynamic diameter, which will always be there, whatever test method you use, but it's just, you know, something you could actually investigate here if you have an aerodynamic diameter classifier. And note that the efficiency of this engine CPC does start to roll off at larger sizes, and that may be an inertial effect in the CPC for larger sizes. And the 3775 itself has a D50 of 4 nanometers, which we haven't taken into account, which will become apparent below where we're measuring here, but may have some effect at this end. The other way of calibrating CPCs, rather than calibrating them back to back with another CPC, is to use a Faraday cup electrometer, which is a way of counting charges, essentially. Now, those of you that know this method will suddenly be thinking, well, why is he going to suggest using an AAC for this? Because you need your particles to be charged in order for the Faraday cup electrometer to measure them. So why wouldn't you just use a DMA? Well, I'm suggesting that we want to use an AAC and a DMA, in fact. You have to have a DMA in there because you have to have hopefully singly charged particles to count in your Faraday cup electrometer. But you want to ensure that those particles are only singly charged, and that's where the AAC comes in. But if you have double charged particles, you'll count twice as many as you actually have. So what we do here is we put the AAC before the DMA and we pre-select a monodisperse aerosol, and then we cut with the DMA from that monodisperse aerosol, and that ensures that we don't have any of the larger particles which will come out with double charges in the aerosol we select with the DMA. And what you do is you can even connect them together with a cable to do this automatically, so that the AAC selects the equivalent aerodynamic diameter as the DMA. We have a Collison nebulizer here with some DOS, a droplet trap, a combustion rotating disc diluters to select an appropriate concentration suitable for both the CPC, which is good for low concentrations, and the Faraday cup electrometer, which is good for high concentrations, so that we can overlap the dynamic ranges and we can dial that in using the rotating disc. We have the AAC and the DMA in tandem and some makeup air, and then the CPC and the Faraday cup electrometer. The good thing about this process is automatable because you don't have to take so much care what your source aerosol is, because your AAC is effectively creating that source aerosol to be any size you like. You can set this up, automate it. You can even control the diluter to change the concentration depending on how much you've got in your source aerosol, and you'd come out with a calibration at the end of it. You would not have to change this source aerosol. Indeed, you can go very high in size here, much higher than you normally can with this technique. Now, you'll be thinking your DMA sort of tops out at about 500 nanometers here. But if you run your DMA very broad with a very low sheath flow, so you're keeping the sheath sample flow ratio still in a minimum factor of 4, which is generally recommended, but you're running the sheath flow down as low as 1.2 liters a minute here. With the top out voltage of this DMA of 10 kilovolts, you can get up to just about 2 microns here. Now, you'll be thinking, well, haven't you just ruined the resolution of the DMA? Yes, but it doesn't matter because the AAC gives you the sizing resolution that you need for accuracy here. So the DMA is a kind of glorified uncharged particle trap in this situation. It's just basically ensuring that only charged particles emerge. So what do we get? Well, it's quite a boring graph, but essentially the ratio between the CPC and this Faraday cup electrometer over this size range, which is down from 50 nanometers to almost 2 microns here, is pretty flat. Okay, the AMS. Some of you will be lucky enough to have an AMS. It's a very useful piece of equipment because it gives you chemical speciation of aerosol particles. It can also speciate by aerodynamic diameter through time of flight. So you can use, while you can use the CPMA, which is our mass classifier to calibrate the AMS's total mass measurement, the AAC is now being used to generate source aerosol of known aerodynamic diameter to check and calibrate the AMS's sizing facility. Moreover, you can just use the AAC as an aerodynamic inlet of any mass spectrometer to pre-classify, and that's an example here from a master's thesis in Helsinki last year. References are given at the end, by the way. Another application, particle charge determination. Now again, this may cause some confusion because the AAC doesn't require the particles to be charged. The normal method, however, of determining particle charge distribution of an aerosol is to select particles by size with a DMA, and then use a second DMA to measure the electrical mobility of those particles and pick out the multiple charge states. This is very complicated though, because the first DMA also generates multiple charge states, and you have to apply deconvolution to separate the charge states from the size selection process to the charge states from the charge determination process. Here we have a paper which has just come out this year on this method for bipolar charger determination. So we select size with an AAC, put a candidate charger in here. In this case, it's going to be a TSI Krypton 85 charger. We then have an electrostatic precipitator, which can be switched in and out to remove uncharged particles, to remove charged particles. We then split the flow either into a DMA and a CPC, which we can then step scan the DMA to give us the, by changing the electrical mobility, count the size, count the charges, or we can, to normalize, just measure the concentration of aerosol with the CPC. Here you can see at nearly 600 nanometers, we've managed to pick out 13 charge states, both negative and positive, from this aerosol, with a very high resolution. Here we can compare a particle charge fraction with the Wiedenhofer charging theory, and we get pretty good agreement. We've also got data in the pipeline that we're going to publish using this technique for agglomerates, for unipolar charging as well. So there's a bit of a paper pipeline there. We've taken quite a lot of data. Finally, I think this is my last application, selection by morphology. Now, what do I mean by morphology? Well, I think I said earlier, there are three sort of standard size classifiers in the world now. There's a CPMA or APM, a DMA, and an AAC. Now, the CPMA selects by mass, the DMA selects by mobility, and the AAC selects by aerodynamic diameter. If you classify by any two of those devices, you lock the third one down. So if we classify an aerosol with an AAC, that locks in aerodynamic diameter. If we classify with a DMA, that locks in mobility diameter. And because those two things are fixed, then mass is fixed. So using any one of these two devices allows us to select aerosols by at least those three properties of morphology. Of course, you could do that with a CPMA and a DMA, but then you've got multiple charging from two instruments, which involves a deconvolution. It's complicated, whereas you only have the one instrument to consider in terms of multiple charging. And Cambridge University put these two instruments in front of some electron micrographs and took some images. So if we select the AAC to 90 nanometers and the DMA to 300 nanometers and put some soot in here, you can see we select these rather nice little fluffy aggregates. If we then adjust the size of the DMA to give us a larger mobility diameter, they get longer. And finally, with the DMA set to 430 nanometers, they get longer still. So you can see we've actually taken these mixed aggregates from a cast burner and sorted them effectively into three different piles online. And so imagine the applications there for things like carbon nanotubes. It's really quite powerful, particularly in the field of engineered nanoparticles. I'm coming to my conclusions now. So the AAC provides a means to select a monodisperse aerosol without charging it, removes multiple charge effects, and mitigates particle losses due to charging efficiency. It provides a means to select a monodisperse aerosol for aerodynamic diameter, if that's your metric of choice. The production instrument has a size range of 25 nanometers to more than 5 microns. We've shown excellent accuracy and transmission efficiency, and it can be scanned to yield a size spectrum. There's a list of references. This presentation will be sent round eventually next week sometime. There's a list of all the papers I've referred to in here. I have some advertisements for forthcoming webinars, dates to be determined. My colleague Chris Nicholas will be talking about the SCS smoking machine for smoking either cigarettes or e-cigarettes or vaping or indeed cannabis. And then, as I mentioned earlier, my colleague Dr. Simon Payne will be talking about filter efficiency measurement with the AAC in much more detail. To register for these, check out www.cambustion.com/webinars or follow Cambustion or indeed me on LinkedIn, and I will send out details when they are scheduled. One further plug, many of you will have heard, I hope, of the Cambridge Particle Meeting, which is a conference that's been held in the summer in Cambridge for over 20 years now. We've, of course, had to change the arrangements slightly this year because of the global coronavirus situation, but we are holding the Cambridge Particle Meeting, and the good news is it will be held online. So many of you who've been unable to visit this conference in previous years will be able to attend. It is, as ever, free. We have a really good program of speakers from all over the world lined up to talk about various particle topics. So if you want to see the schedule and register, go to www.cambridgeparticlemeeting.org, and it will be held by Zoom on the afternoon UK time of Friday the 19th of June. So quite soon. I hope to, as it were, see many of you there, as it were. Okay, I'm done for now. Any questions? And I can see I do have some questions. The scanning mode, so the time for the scanning mode. So it obviously depends on the size range that you want, but you specifically asked 25 nanometers to 5 microns. So there are up scans and there are down scans. There's a physical spinning classifier here, and it's limited by the time taken to speed that classifier up. So if you're doing an up scan, which is when you start at from a standing start and you increase the speed, so you're actually going from large particle sizes to small particle sizes, for the full range of the instrument, that's probably about 7 minutes. If you're doing a down scan, that's quite a lot faster. It's maybe about 5 minutes. The thing that slows it down is the small particles. So if you're happy to do a scan from 100 nanometers to say 5 microns, probably halves the scan time down to about 3 minutes. But because you have to speed up the classifier to get those smaller particles, and it's a rather sort of exponential relationship between those two things, that's why you get to the really smaller particles, that's what slows it down. So if you're happy down to 100 nanometers, probably 3 minutes. If you want to go down to 25, probably more like 6 minutes for the up scan and about 2/3 of that for the down scan. The reason being is that friction helps you. The friction of the bearing, such as it is, makes the thing slow down faster, essentially. And that's compared with the step scanning, that's good 2, 3, 4 times quicker. So the step scans could take, it depends how many points you put in. It could take forever, frankly, if you put enough points in. But 20 minutes, half an hour, not uncommon. This takes it down to a matter of a few minutes. We've had a question here saying, do we not have representation in the USA? We don't actually. We've sold many hundreds of instruments over the years to the US. We travel to the US an awful lot and attend conferences there. We manage to serve the US pretty well from the UK. It may be our shared language, I don't know, but we seem to manage to deal with the US fine at the moment from the UK. So yeah, and there are indeed many AACs and CPMAs in the US. Question, can I upgrade my existing AAC to do the fast scan? Yes, you can, and it's a free upgrade. If you just send me an email, I will send you a file to upload to your system. Obviously, we always recommend that instruments are serviced regularly, but this can just be applied by the user. It's just a software upgrade. And you can also, if you want to, revert back, and this is just an option in the software to go back to doing step scans. There are sometimes when you do want to do step scan. For example, if you're not actually doing a traditional scan, but you're actually using your AAC to supply an aerosol to another device, and you want to just vary that slowly over time, do a step scan. That'll do that for you, but you can revert back. But yeah, software upgrade is available and free. Okay, I have a question here. Does the orientation of the particles, assuming that it's a regular shape, affect the particle transportation loss in the sheath flow? Not that we can see. because the particles are small compared with the physical dimensions of the instrument, that's probably not an effect. We've used this instrument now, and our customers have used the instrument now with all sorts of morphologies, and we haven't really seen any difference. Another question, I mentioned the AAC could determine the mixing state by determining particle density. Do I have any material on that? I don't actually have any material on the AAC being used to determine mixing state, because up till now the CPMA has tended to be used. So I've got material that I can send you on the CPMA being used to determine mixing state. Particularly in China, there's been a lot of work around Beijing using the CPMA to determine the mixing state of the black carbon in the atmosphere. But it's just saying that the AAC can be used for that, and it doesn't involve so much of a multiple charge correction. It's just there are more CPMAs in the world because it's an older instrument, so people are tending to use that at the moment. But I can certainly send some information on mixing state measurement. And indeed, we've got a toolkit for the CPMA that does some of the data inversion for you. And yes, we'll be sending the presentation out afterwards, both in video form, and if anyone wants the PDF, just drop me an email and I can send you the PDF as well. That's fine. Okay, well, it looks like that's it for the questions for now. I hope everyone keeps safe, and I hope eventually we'll be able to meet in person at some point at one of the conferences or your site in the future. I certainly look forward to be able to travel again. But for now, I'll wish you a good morning or good afternoon in many cases, and thanks very much. And Chris has put some links in the chat there, by the way, to the Cambridge Particle Meeting and the AAC page for those who are interested. I hope to see some of you at the Cambridge Particle Meeting via Zoom. Okay, thank you. Have a good day.